Hi, my name is Nick, and I'm here to present the solution to problem C, broken minimum spanning tree. In this problem, you're given a labeled spanning tree in a weighted graph. In one operation, you can remove the label from one edge and then add a label to an unlabeled edge. Under this operation, the labeled edges must always form a spanning tree. Compute the minimum number of operations needed to make the labeled spanning tree a minimum spanning tree of the graph. The bounds are relatively small in this problem. The number of vertices is at most 2,000. The number of edges is at most 3,000. So first, we'll tackle a simpler version of the problem where the edge weights are unique. In the event that the edge weights are unique, the minimum spanning tree is unique. So if there are E labeled edges that are not in the minimum spanning tree, then we know that we need at least E operations. However, we can always do it in E operations. Just pick an arbitrary edge that isn't labeled and add it. You now have a cycle, so you can remove the heaviest edge in the cycle, and this edge can never be in any minimum spanning tree. So to solve the original problem, the edge weights are not unique. So over all the minimum spanning trees to consider, we should pick the one that maximizes the number of labeled edges initially present. When we're trying to find a cycle, just DFS from one vertex of the added edge to the other, and then when you return from the DFS, in the DFS tree, you'll have a path from or between the two vertices, and then you can just pick any edge from that spanning tree that isn't in the candidate minimum spanning tree.